Good morning, everyone. Okay, it's recording. Okay, so last time we stopped at my MATLAB file devoted to trees, dendrograms, and how to work with graphs in MATLAB. Okay, so we generate a set of 10 random points in 3 dimensions. Discuss the command pdist, calculating Euclidean distance between pairs of observations. Then we transformed this distance vector, a list of all distances, long vector, n times n minus 1 divided by 2. Transformed it into a square form, so it's a distance metric. So if you have in course of your study or work research, you find a distance matrix, you could just immediately start from this point, assuming that you have a squared form. Then we perform the linkage of between this set of points with respect to a particular algorithm. Linkage generates a set of auxiliary points required to construct a dendrogram, branching points, right? Then we draw this dendrogram. And now I want to discuss actually a data which had been taken from the paper I sent you in the package last time, concerning this oscillator graph. So basically there is a bacteria, and researchers studied the proteome of this bacteria, and they discovered that some properties, I don't remember what, and I was not interested in that. Basically, I'm not a biologist, so periodically the bacteria exhibits in its behavior some alternating properties, kind of oscillations. And the idea is that maybe it is related to some genetic mechanisms, running in parallel. And the idea was that, okay, apparently a particular set of genes responsible for the behavior is activated through 2 different paths, and these paths have different lengths. So we have a competition, and then and this competition generates oscillations or responsible for observed oscillations. Indeed, it's a kind of hypothesis, but nevertheless, it's the way of thinking about nature. Well, okay. So, the database is called oscillator graph. So I load it. It gives us 65 by 65 graph, which of these proteins somehow involved in the process. We can draw this graph with using a special command SPY. Why is it important? Because the SPY works equally well for many 100,000 nodes. If you have a large graph, well, I never checked whether it works on millions, but it works for at least 400,000s. And you could see the structure. The structure is symmetric in principle, so there is always bilateral connections. Okay, just to show you this very useful comment. Now I just take names for these proteins. Customer gave me names, so I just collected them here. And now I'm going to draw this graph. Okay, I draw this graph. So this is the graph they provide us. And now we should take, so you could basically use these routines in order to draw annotated as well as non-annotated graphs. Annotated means that they give the vertices nodes given names of these proteins in particular, but you could draw with the standard procedures any graphs you like, and they might be symmetric and so on. They might be directed, and well, now I should color the proteins which believed are responsible for the processes. Okay. Yes. So these are 3 proteins. PA believed to be a starting protein which is influencing a protein C which is responsible for the particular behavior. And then you could imagine that there is one path direct from A to C, and then there is another path through B. And that is why these 2 paths compete and create oscillatory behavior. So this is the idea. Okay, very nice. You see that if you have only 65 nodes, in principle, I can show it to you by just showing you the picture. But if you have hundreds of 100,000 nodes, you are not able anymore to say what's going on there. Okay, so these routines might be useful for study very large graphs. Okay, yeah. Now I want to find the shortest path. So my hypothesis was, or not mine, but the authors of the paper I sent you, hypothesized that there are 2 paths which compete with each other. So I should find one. Okay, I try to find the shortest path. Okay, and I colored them. So I should have, yes, this is my shortest path. There are 2 sequences of comments. I separated them because indeed I can find the shortest path, but it's just, in fact, if you open this object, it's just a list of, a sequence of correspondences. And now in the second step, I always should visualize it by red, for instance, right? Highlighted this path by red. Now, I should find some alternating path, and I'm really happy why I actually chosen this example, simply because there are only 2 paths. And I can use the simple common traverse in order to find all available paths between nodes. Because if I would have many, then indeed it might be confusing. And now I'm going to, yes, find an alternative path here. And I found an alternative path, a blue one. And there is also should be, well, in principle, if I want to find all shortest path, I just can generate a matrix of all possible paths. And now I want to somehow to visualize it. And one example how to do it is through constructing a matrix of distances. The matrix of distances, all shortest path in a network. I have 65 nodes, and my path ranged from 0. 0 is, well, on the main diagonal, it's a distance between node and itself. Okay, so which is obviously 0, up to basically 19 here, which well, so this is the, so to say, kind of a characteristic of a structure of a graph. Now I want, since I know, you see that, well, basically I constructed the matrix of distances. In my case, distances are just graph theoretic distances, number of hops from one node, every node to any other node. I can construct a dendrogram using the method we discussed last time. Okay, in this case, I have 65 nodes, not 10. But again, I have a distance matrix, and every distance matrix, so it generates me a tree. 42 and 44, don't be confused with commas and with points and zeros. These are integer identification numbers of vertices. Okay, and these are distances. Some of them are not available. Nevertheless, I also performed a linkage and generate the dendrogram. That is. Okay, so whenever you have a distance matrix, you could draw a dendrogram. Okay, so that's what I wanted to show you in my MATLAB file. So please, whenever you need iterations like what we discussed, use these pieces of code, and you can just perform your own study research of networks. Now I would like to start with what? With next presentation. I stop sharing screen. Yes, oscillator graph included in MATLAB. Okay, so there was a question. Yes, it's included in MATLAB. Well, along with many other databases just used for training. Okay, so you could read the text, and you could also study this graph yourself. Okay, now, what should I do? Yes, now I want to go to 11. Yes, I'm opening folder 11. Now I share screen. Okay, so folder 11 contains 3 files. First, it's a presentation for today. Presentation, I call it complex networks. So, but the story is the following. So people started to draw trees for different distance matrices. So whenever you have some distance, means geometry, you have a tree-like structure which represent data structure you are interested in. So people started to represent structures by trees. Surprisingly, it's happened 20 years ago. On my eye, basically, I saw it. And they discovered that if they try to visualize data structures from real world phenomena, analyzing the structure of roads, phone calls, internet, friendship networks, and many other examples, they observe these trees do not look like what we have seen in my toy examples. They are very heterogeneous. At every node, there might be, a fork, but not 2 or 3, but, 50. Oh, it's a kind of, citation network or popularity network. In, these video blogs, for instance, or in social media, we have, or in Twitter, we have hubs, social hubs, really people who attract, some celebrities, or I don't know, president of the United States, or somebody else who attract a lot of other subscribers, followers. Okay, so if we just interested in distribution of number of followers, we would observe that there are relatively few people with a huge number of followers, millions, or maybe tens of millions, I don't know. And well, a lot usual regular people which have maybe their family members as a single set of followers, if any, or just staying alone. Okay, so this is the major point what actually issue which attracted the attention of researchers during the last, say, 20 years. They named the net of trees which generated in course of analysis of real world systems. They call it complex networks. Okay, so we will discuss today complex networks. Now, also a second file is graph theory package of Maple, which we will work out. It's just kind of counterpart of MATLAB stuff, but in Maple. And what is important in Maple, it's made for mathematicians, so it might produce objects like chromatic polynomials and other things which are not mentioned in MATLAB. However, if you want to perform a real numerical work, you know, analyzing of thousands of events and so on, MATLAB is indeed is the major computing environment, but for mathematicians, Maple is maybe more important. And also I provide you the manual for graph package in Maple. So there are a lot of useful comments, and you might just surf over it when you have time to get an idea of what you could do with Maple. Okay. Now I start with my presentation. I'm not sure whether I would be able to finish it today, but nevertheless, okay. So I should somehow, no, share screen. Okay, so I stop sharing and then I share it again just in case, to be sure that you really see my slides. Display settings, duplicate. Right, now you should see it. Okay, well, but the story, well, okay, so we have a network, what we call a complex network. We need some, well, people did not work with this entity before. So first step of every research is to find some appropriate tool, a toy model, for using which we can understand the property of the new entity. Okay, so the tool for study of complex network is random graphs. Random graph is a model invented, well, proposed, put forward by Erdos and Reini, they are Hungarian mathematicians, in 1959, actively studied during 80s, 90s. Well, nowadays it's a little bit out of fashion, but a lot of things was understood about the structures, was understood by studying these random graphs, because many things could be calculated explicitly if you know probabilities of some events. Okay, so what is a random graph? So there are a set of nodes, and we believe that they are connected by links purely at random. What is the most important thing? If I just have a set of points and then I at random try to connect nodes, what do I see? In fact, the red edges becomes more and more dense, and the important question might be when most of nodes will be connected into a single giant component. So the term is here a giant component. There might be, you see that there might be three micro components which contain a single edge, connecting a couple of three couples of vertices. And then there is a giant component which incorporate, say, tens, or later, if I still inject edges into the system, finally, sooner or later, it would happen that the whole, I mean, I would get the completely connected, well-connected graph. So the giant components takes over the whole graph, okay? Well, the process would continue, and then finally at some stage I get a complete, you see, a picture where every node is connected by assimilated by the giant component. So the general observation is that the general observation is that there is what physicists would call it, they call it a phase transition. Before, nodes were unconnected, but then after some value of critical parameter or order parameter, how physicists would call it, something happens and the structure appears which incorporate all nodes in the graph. The order parameter here is average number of links per node. It appears that once I'm injecting one link at one edge at each time, and then after n steps, where n is the size of node, in average, I would get a single edge per node. And at this very moment, a giant component pops up, emerges, and in a very fast way, it takes over the whole graph. What people were studying the connectivity properties of in this giant component. They learned that in this giant component, we can measure, since everything is connected, nodes are connected, I can measure distances, okay, number of hops between any pair of points. And I can take, since the graph is random, I can calculate an average length. And it appeared that average length, expected length between any pair of points in a giant component of a random graph behaves as logarithm of n, where n is the size of nodes. So this is the property. Why is it important? Because we then compare real graphs, which are certainly not random at all. We compare them with the properties of random graphs. And we know that actually, you see that the distance is a logarithm of n. If n is, say, 100,000 or 10,000, it means that it's a logarithm of 10,000. It's relatively, and on the other hand, at the end of my talk, we will discuss Milgram experiments, 6 degrees of separation. You probably know this media phenomenon, right? So that everyone is connected within a society, is connected with everyone with approximately just 6 handshakes. You see, it's completely different properties. So probably this heterogeneity, special structure of real-world network are required to dramatically reduce separation degrees. Number of handshakes required to reach say 2 individuals. In a society, it's believed, at least according to experiments in 60s, made in 60s, we have about six hopes in between any of us, 6 hopes to the president of the United States. I'm just joking, okay? But in a random, so the graph is not random. So it might be used as a measure of non-randomness. So this is the idea. The first important is the average length, the average distance. Now, Originally, in Erdős-Rényi model, published in 1960, they just proven that if we analyze the degree distribution probability, so what is the probability that a node has precisely degree k? Degree is a number of neighbors, number of neighboring nodes. This degree distribution follows a Poisson distribution. So basically, it's an exponent with a negative, with some negative, with average number of average number of neighbors, with average degree. It tells me that if I would like to observe a node with too many neighbors, the probability of such an event that I would succeed in finding such node goes to 0 rapidly, following an exponent. Well, asymptotic behavior of large path lengths. Well, before random graphs, people knew lattices. You know, lattices is what you might observe in your copy. Well, I don't know, in the United States, there is no these copybooks with regular grades. Well, you probably could find it somewhere, but not in Walmart. So it's a typical lattice. In lattice, the length of the path depends upon number of nodes and the dimension of space. So it's a d order root of n. In random graph, the average distance grows as logarithm of n. Okay? In principle, it means that logarithm of n grows slowly. You see, the logarithm is weaker than any power. So it grows slowly. So it was clear that new object random graph is something different from what people used to think about. When we think about atoms or whatever, we think about crystalline lattices. And this was the mindset till even after the Second World War. Graphs are those lattices, they are symmetric. Platonic solids, very nice looking symmetric bodies. Okay, so it was a new object. Another feature to study is a clustering coefficient. If I consider a completely connected graph of how many? 5 nodes, I have 6 edges between them. In reality, if I consider a graph, I might observe that it might not be fully connected. That means some edges might be absent. There might be no particular edges. And the ratio of available number of edges and the total possible number of edges, which might be if the graph was fully connected, is called clustering coefficient. How dense is our graph, so to say, right? So it's a number of links between neighbors divided by number of links in a fully connected graph, n times n minus 1 divided by 2. It's a binomial coefficient, Cn of 2. Phenomenon which is related, real world phenomenon. Friends, your friends in Facebook or I don't know where, you see that one guy has a friend and he make a friendship with another guy. Sooner or later, friends of one guy becomes friends of another guy. Because they comment each other. They watch comments, they reply, and so on in a very rapid way. There is a kind of, dense network of comments which results in establishing some friendship relations, even with people whom I never saw in my life. Most of my followers in Facebook or elsewhere, I never even have no idea of them in real life. Okay, so they had been taken from my friends as friends. Okay, so this is precisely what we have in data. the clustering coefficient of the data structure is always growing with time. The only reason how to stop this avalanche, like in Facebook, you know that the limit of number of friends is 5,000. You cannot take more friends, I mean, accept more friendships, and you cannot afford more friendships if you you know, reach this limit. And this is precisely the way how to stop the process of growing indefinitely. The more friends you have, the faster you acquire new friends. Okay, yes. The same thing, citations, citations in scientific papers. What for do we cite each other? Absolutely. Well, typically we mention trivial facts and then put some citations. It's done simply to establish kind of relations. It's, you know, like a Facebook, but in old times, this process was not a matter of minutes or hours. Now in Facebook, you just should make friendship with several important people, and then, well, in a week you might reach this 5,000 limit easily. Before, in old times, it was not possible, and these publications play the role of this social platform. Publications in different journals, but were just few journals till 80s, 90s. Physical Review, a single journal for physicists in the world. Whenever who is publishing there, he's a physicist. So once he cited somebody, those guys, well, being attracted by these citations, well, they established some relations or believe that they are friends. So it was the same mechanism, precisely. It has no any particular meaning from the point of view of real research. It's establishing of private relations. And therefore, all these editors are very angry if you cite some guys like Lagrange or some guys who lived many centuries before, because they are not present in the community. Okay, so that is clustering coefficient. And what is about asymptotic behavior if we compare lattices and random graphs? In lattices, yes, in lattices the clustering coefficient is constant. Why? Because we know precisely what is the dimension of space. Therefore, it perfectly determines the number of neighbors in a lattice. In a random graph, it decays with n. Clustering coefficient decays with n. What does it mean? It means that, okay, so the more nodes I have, the less is the value, the less dense it appears to be. So asymptotically, if the graph is very large, I get a tree. Random graph is always a tree. A huge random graph is always a tree. A probability to get an auxiliary connection, pairing, or some auxiliary path, you see, in competition with the given one, in a random graph, is vanishingly small. It's zero if n is large enough. If the graph of proteome of these bacteria, which we discussed from the very beginning of today's lecture, if it were random, there will be no any extra path. There will be no any oscillatory behavior. Okay, so as I told you, all types of these phenomena, if we summarize them, we might observe something which is drawn here. Please pay attention that the graph is in logarithmic scale, in a decimal logarithmic scale. My equally distant labels are 10, 100, 1000, 10,000, and counts of events is also 10, 100, 1000, 10,000, 100,000. In a logarithmic scale, these hierarchical networks, complex networks, follow one and the same pattern. They produce a line, a slope, a single slope, saying that there are many low degree, few high degree nodes. Well, sorry, few high degree nodes. It should be, yes, okay, I reversed it, but okay, so many low degree nodes and, okay, so not the, I confuse these squares, you see. Yeah, so what should I say? That we have very few popular people. We might have very few popular hubs, transportation hubs, but there are many small airports, many small bus stations, and so on. Okay, so this is the natural idea. But if we draw it in a logarithmic scale, with a very high probability, we observe something which gives us a slope. And the idea was, let us compare the slopes. Some slopes might be very steep, other might be, well, not very steep. And some pictures about, about internet, 1998, I will show you some pictures later. And another feature of these complex networks, if you look at the graph here, you would see that as if this distribution has a fat tail. The synonym for complex network is a fat tail network, a distribution with a fat tail. You see that here, the right-hand side tail becomes wider. Well, actually, it's a during the 15 or 20 years, people were focused to this to the slope here, and they did not pay attention to what's going on here. But here, there was an explanation of what's going on here. In fact, what do we have? In fact, now we know that there are no such complex network, scale-free complex networks following an exact power law. There are many, many, many random graphs, which follows, all of them follows Poisson law. But since there are many, when we observe them, we perform an integration. If we integrate a Poisson law, many Poisson laws with different average case, average number of average degrees, we would get a power law. Very simple mathematical fact. Known since, well, I don't know, 19th century. In all integral table, you might find the appropriate integrals. But what's going on here? In a fat tail, we have not enough data, and therefore, we have many, many, many different slopes. They are still here, visible. So in fact, if you observe a complex network, it means that there are many systems operates on this in this space. A good example. Good example. I jump. Yes, well, I will show you these pictures. Yes, so these are these integrals. This is a Poissonian distribution. If I integrate with respect to different k, I would get something of order, some parameter, some constant in power of n plus 1. Some constant in power of n plus 1. So this is my scaling. This is a zip flow. It also goes from here. If I consider a network of roads in the United States, organized by whom? A Department of Transportation. A single entity. They planned their network. They planned it. A single guy who had planted it. Or maybe, I know, a single institution. And the distribution is Poisson. If I have a set of air travels organized by number of companies, flights, I have a power law immediately. Because, well, each company produced something like that, but then I integrate all these Poisson distributions together. And if I am not going to discern between different companies, I get a complex network following a power law degree distribution. So this is the message. That's what we learned by this time. Okay, but before we understand that, there were a lot of examples. East Proteome, this is Manhattan, the number of each street, how many street so every street in average connected to some, well, number of some other streets. This number varies, but we might have nevertheless some slope in logarithmic scale. Internet, some proteomes in different bacteria, melanogaster, it's a worm, elegans worm, Wikipedia, and so on, business ties in United States, branch of United States industry and technology, structure of organizations, friendship networks, collaboration networks, terrorist networks, airlines, okay, genetic interaction networks, and so on and so on. So during this, so they wanted to, people wanted to explain, well, from where this complex network story with power law degree distribution might come from. And the most important impact in this in this direction was made by Barabasi and Albert. They proposed in 1999 so-called preferential attachment approach. Suppose you you make an account in some social network like Parler or Telegram or, you know, Facebook or whatever, and you make your first steps to I mean following, choosing somebody to follow, and with high probability you would follow somebody with already have a lot of friends. It's a popular guy. It's a social hub. You would find, you would even among your friends, you first follow a guy who has the most of friends. I mean, it's a probabilistic process. So they try to express this idea, putting forward an, it's called a linear attachment, linear preferential attachment principle. We have a number of nodes, friends, K, and the probability that a newcomer would follow you depends upon the total number of your neighbors, your friends, divided by the sum of all friends in the network. How relatively important you are in your local friendship community, in your class, okay? So they simply assume that there is a, well, suppose that the more friends you have, you know, it's called the Matthew principle, in fact. Those who are talented and gifted and have more money would get more money, even more money. And those who not, it's a probabilistic process, but in fact, well, the probability to get some would be very low. So this is the simple principle. Since it's so simple, it's possible to calculate the asymptotic probability to get K friends, and it follows, you see that we have its proportional, probability is proportional to K, 1 over K in power of 3. Because K times K plus 1, K plus 2, if K goes to infinity, finally I have K in power of 3 cube. And these cubical slopes are ubiquitous. Well, then, but some of them are not, simply because Poissonian laws sometimes integrated with different weights, now we know. And they started to, you know, to introduce some alpha, or they call it fitness, some coefficients, which might, you know, so that some individuals are more attractive than others, and so on and so on. Nevertheless, they started to, they were able to basically to forge any slope of the real, of some real systems. Everything was fine till this SARS epidemic, which year it was, last time? Swine flu in German. So, well, I don't remember, 2006, no, 2006 or 2008 or something. There was an previous pandemic, kind of pandemic situation. So they started, I mean, these guys say that, okay, so we immediately now make this, or construct the models for data using these graphs. They produce these models based on their methods, and they didn't work. And it was the end of the story. They lose a lot of money because they create a model of epidemic spreading based on their scale-free graphs. And the model didn't work because the epidemic spreading had completely, I mean, what we had really observed was completely different. Nowadays, you know that even nobody claims that they are able to make a model of COVID epidemic because everyone is already very clever. It could not be described in a simple models like that. Okay, but that's what I wanted to tell you today. Probably that's, yes, formally it's, yeah, but yeah, let's discuss Milgram experiments and the topology next time. Okay, and then, well, we can still have some time for topology, but just maybe if you study the earlier characteristic of a graph, if you study topology, you might know that, well, in principle, there are some simple mathematical quantities which allows us to judge the structure, I mean, of a surface or a graph, and in particular, how many handles it has, what kind of, is it a compact or is it a hyperbolic? So this is a so-called crochet manifold. Crochet in French means knitting manifold. Well, it's an example of hyperbolic surfaces. Well, and in principle, if we think about these complex networks, random trees, huge trees, with a power law degree distribution, inevitably we get into hyperbolic geometry. It's already a tree, you see here. It's a tree-like structure. So the idea was that let us use hyperbolic geometry in order to navigate in complex networks, like in the internet. Well, we basically observe now that different countries start to split, creating their own zones of internet zones, which are loosely connected with others. It was a solution provided by the network itself. Some people tell that this is because of, you know, lack of freedom of speech, blah, 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 something else. But in fact, technically, it appears that the internet is too large to be self-sustained. And then it appears that, I mean, the solution comes from the network itself. But before that, the idea was that we can make an efficient addressation, internet addressation structure. The problem is the addressation structure. Well, there are different types of addressation. If I take my phone, I call somebody, we have a connection all the time while we're speaking. Nobody could connect to my correspondent, okay? This is one type of addressation. Another type of addressation was used in the internet. We split a message into patches, and these patches might go different ways through New Zealand, I don't know. Because if some connections are lost, it nevertheless might find a way. And it's out of control, basically, because the routers every router on the path, it's kind of greedy algorithm, kind of Dijkstra algorithm. It search for, okay, what's written in hidden in the header of a message, Japan. Okay, where could I have only channel to Australia, so I send it to Australia, and then from Australia it might get somewhere else. And the router decide, a lot of routers decide what should be a traffic, I mean the optimal traffic. And there was no, and still there is no, even now, an optimal authorization scheme algorithm, which might make which might make the internet reunited. And indeed, as internet is growing, it becomes more and more, how to say, patchy. The word ghetto. China has their own structure. Russia has its own structure now. Europe is going to be somehow barrier, I mean, make a barrier between themselves and the United States because they don't like what the United States is doing, especially, and so on and so on. We have borders, I mean, walls on the borders. We have walls in the internet. So that's what I wanted to say, to explain you today, and we will work out the examples next time. Thank you so much. I stop sharing my screen. And yes, and stop recording.